So, you will recall that we just started discussing about electrostatic precipitators, okay, and which you see it from inside, but before we go inside this one, let's little bit talk about the theory that why ESP, why talk about ESP. See, you also will remember that I showed you that how the difficulty in removing the particle was related to the diameter of the particle, okay. And we said, well, if you're just applying the gravitational force or cyclonic force, that difficulty will be the diameter square, okay. So, when the particle reduces, we want to remove the smaller particles, and with the forces that we studied, that was the gravitational force and centrifugal force, those were not enough, okay. Those will not remove the smaller particles. So, we thought, why not utilize the surface characteristics and use the electrostatic forces, okay, and utilize that one, because that driving force will be proportional to the d rather than d square that we showed you. So, one of the ways to use electrostatic forces is to charge the particles, okay. But before we go into that one, I was just showing you, if these are the plates, they are parallel plates, there are many plates, and in between plates there is something, okay, and that will be used for charging the particles. So, I will draw a little blow up picture of the tubes, and the pictures looks okay. So, these plates, as we said, are grounded, okay, and in between these plates, okay, let us say we draw some kind of beam or something through which I can hang the wires, okay. Like the one wire I am hanging is okay, and put some solid bob or like a pendulum, but it doesn't move, it cannot move, okay. Okay. Now, I can have several of these plates, like in parallel, several of the hanging wire with bob, okay. So, this is what we called as the collection plate. That is what you see in the picture. You are really looking at the collection plate, but you are not seeing inside, but you see from inside. Then there is this is called charging electrode or something. Okay. Your dirty gas, okay, is entering in between these two parallel plates, okay. What will happen, and the voltage difference between the plate and this electrode is about 40,000 volts, okay. So, the voltage difference, okay, kV, okay, and this is negatively charged generally. It could be positively charged also, but generally it is negatively charged, okay. And the kind of distance which you are talking about is about 3 to 4 inches, if I can say, between these two plates. Okay. Now what happens is, now your thing is filled by the dirty gas with the particles and everything. There may be some electron, okay, which will, or as I was trying to show you yesterday, was okay. So the electrons, there will be some stray electrons that is there in the gas stream or something. We always find some electrons in there. So these stray electrons, they'll, once they see the negative charge, they'll be accelerated away from the electrode. They want to run away, okay, because they're being the same charge. In the process, this acceleration is so much, okay, these things hit to the gas particles. And remember that this is happening very, very close to the electrode, only we are showing it a bigger picture. So this thing in the process can knock off some more electrons from the gas as we are going away. Again, they can knock off more, okay, but as they go away, they also lose their energy because they are getting far from there, okay, and numbers will reduce. And but this can be very significant, very close to this thing, very close to your the electrode. These gas particles will become positively charged, and what they will do, they will rush towards the electrode and get discharged, right? But the electrons which are got free, they will continue to move away from this one, but their energy will reduce, okay? Once their energy is reduced, they cannot do more charging and knocking off of the electrons from the gas particles as we go away. But in this area, they will do a lot. But once these electrons, they are become freely traveling, and once they encounter your, okay, their particle or dust, then they can sit onto the dust particles. Okay, so these electrons can sit onto your dust which you want to remove. So in the process, what happened? The dust particles have become charged because they are keeping, or the electrons are piggyback onto them, you know, they are just sitting on back of them. So now what will happen once they are there, okay, your dust particles, then this dust particle will also start traveling in the direction opposite to the discharge electrode and go towards the plate, because they were going towards plate anyway. The electrons, they have to go towards the plate, but on the way more electrons are become available, and then they sit onto the particles, and then they are able to, the drive is continue towards the plate. So as a result, all the particles start moving from wherever they are back to the plates. So they will go, and the moment they hit to the plate, okay, they will discharge and they will stick to the wall. So this is the mechanism, this is how this happens. So remember that ionization is taking place only for gases, because sometimes people get confused, oh okay, they hit to the solid particles or dust particles and particles become charged, okay, where are the electrons coming from? But that's not the case. So thing which is getting charged is the gas, okay, which is the air generally, or the flue gas, and then the more of the electrons come out, and these electrons sit onto the dust particles, and then these dust particles, they continue to travel because of the charge they are carrying towards collection plate, and then they go ahead and sit onto the collection plate. Okay. So is that part clear? Okay. What happens, if you recall, if there are lots of electrons that are emerging out, okay, so there is something called, if you will remember, a word called corona effect. Okay. So there will be some kind of corona effect that will take place. So more and more electrons are coming out, and if you suppose in this one you had a little glass thing and you can see a dim light, okay, because of the corona effect onto this one, and you can see, you can really see some kind of dim light across this one, okay, means electrons are being discharged very quickly, okay, and that is what you call as the corona effect. And as long as, if you can see some of the ESPs, they do have this kind of thing that you can see through the glass, okay, at least some of the experimental one, and you can see the corona being generated, and that corona is key. If the corona is not being generated, it means your ESP will not work, because you are not producing enough electron. Those will sit onto the particle and drive those particles towards the plate, okay. So this is the mechanism which, or this is the physics if you like. Then there are mathematics for this one that we will see or probably will not see so much in detail, but I want you to get the sense of the thing, okay. So once these particles come this one onto this one, and as they will travel, they will sit onto the plate, okay, and you see very quickly these particles forms a cake onto the and then these particles will form cake onto the plate, okay.
It is required that dust must also be charged, positively charged.
Dust need not to be positively charged. Why dust should be charged?
So what is the mechanism of electron being attached to the dust?
Okay, the electron, as they are moving away from there, they have lost more or less their energy, okay. They are traveling slowly, okay, and as they encounter the particles, they get stick to it, okay, just physical sticking. They are not necessarily knocking off anything from the particle. They don't have that kind of energy that it can knock off something from the particle and sit there. So simply what you will see here, as the particles of your dust, they are going, they will look something like this. Your dust and some electrons sitting there. Simply attached, okay. So now in the sense that electrons are sitting, it becomes negatively charged, okay. Nothing from the inside or nothing at the atomic level, okay, but then they are just sitting onto this one, and then as a result they will, these particles which were otherwise going straight, okay, they tend to have a migration velocity towards the plate, okay. So this is what happens. So now this effect, you see the corona effect very close to this thing, and then these particles will form little cake onto this one, okay. So this is what is the thing, and as we go a little away, it become more and more, the gas become more and more clean. We will see this one. So then what they do is, after this one, once this is there, for every field, this is called one plate, and this the charging electrodes in between, this thing is called one field. It's very common to have 5 fields, 6 fields, 4 fields to remove the particles, because in the successive thing we will see that one. And once these are there, underneath this one there will be a hopper, okay, and then there is some operation called wrapping operation, RAPPING, wrapping operation, okay. Wrapping operation is, what we do in the wrapping operation is, there is some kind of hammers, okay, which are like with some mechanical movement, they can come and hit to the plate, very hard, hit to the plate, then again they can come and round, hit to the plate, and once they hit to the plate, the dust will fall in the hopper, okay. Otherwise dust can be sticky and then it is not falling. So that with the wrapping operation, you can basically, wrapping operation, what happens in the wrapping operation is just again the inertia fundamentals, okay, because this plate is stationary, the particles want to be stationary, dislodged, and they continue to fall in this. So when there is a wrapping operation, there is a good chance, okay, that your emission at that moment will increase, because the gas, this is all continuous process as the wrapping operation is going on, and then, but that will be for few minutes, like maybe you may need to do the wrapping operation once in 24 hours, once in 8 hours, but then that time the emissions can be little bit large, because you are de-dusting the whole ESP in a sense, and then you can, when the wrapping operation is going on, okay, you can hear the sound, okay, that hammer hitting to this one. Like for example, an ESP, even for let's say 50 megawatt power plant, can be size of this room, okay, and then the huge plates are put inside, and you can think of as if the fans are the discharging electrodes, Okay, you see the fan and I hang there and then this goes on. Okay. So you see here the few things which we have talked about more in the terms of the physics is these are the metal collection plates. Okay, particulate laden that gas goes in there, and then the gas which is smoke free, it comes out. There is high voltage power supply for the charging electrode, as you see there. There is 40 kilovolt. There are rectifiers. Okay, there is a DC voltage that is supplied here. Okay, and then you see the wrappers. Okay, the mechanism that will hit to the plates. Okay, and these are called field number 1, field number 2, field number 3. Okay, but once they do the operation, and it's all computerized, when they are doing the wrapping operation in this one, the wrapping operation in this and this cannot start at the same time. Okay, otherwise you cannot put the whole thing under wrapping and then you will see emission being very large. Okay, so once the wrapping operation is going on this one, these are fully operational. Okay, so dust that is emitted here, 99% of that will fall in the hopper. Whatever little which is entrained back into the system, that will be collected here and here. So most the emission you only see when the last field or last plate is being wrapped. Okay, but then you will see here this, because most of the collection will be here followed by this one, and there will be a minimum collection here. So then that part is not so significant. Okay, so that part when you last wrapping operation, this requires very rare once in, let's say, 24 hours or something. So at that moment you can see, sometimes you see a very good plant, you say chimneys you see working fantastically, but on some stray occasion you can see that, well, there are some emissions. Okay, so that emission could be either because of the wrapping operation or something going wrong, but then it could largely be because of the wrapping operation, because the entire process is very robust, it works very fine. It does not work under certain conditions that we will see in a moment, but by and large it works. So the application is so good that you have the large power plants, okay, where you have 6 fields, so you can see the 6 rooms, 6 room of this size, okay, and things are going continuously, and it can be as small as it can be fitted into an air conditioner. Okay, you see this air conditioned advertisement you see all over, oh, this is a clean air, this is a bacteria free air and things like that. So they may have some device, okay, and ESP is one of the device which they use inside. Okay, there could be filter or some of the things they use in the ESP. So you see the common air conditioner, you are seeing it might be fitted with a very small, but not the same kind, different kind of this thing. There you go. So you are not only you can remove the particles, you can also remove, let's say, mist or the liquid particles in this one. Okay, so then it's called wet ESPs, but mostly it is used for the dust one. So what I'll do is that I downloaded some picture for you. Let's say if you can see that one. So this is what a typical ESP will look like with the 4 fields. Okay. So you have the transformers and rectifiers fitted onto the top, the field number 1, field number 2, field 3, field 4, and generally they run in the parallel. Okay, because you see here the gas quantity may be very large. Okay, you don't want to have too much things, okay, one large thing rather than you divide into. The idea of dividing into a parallel process will always have the higher efficiency. Okay, if something goes wrong in this stream, okay, things go wrong and things can go wrong, so you continue to operate this one. Okay, so that's why generally you will see that the 2 ducts from the same let's say generator, they'll divide in 2 streams. One is going in this one, absolutely identical, but one will go in this one, the other will go in this one, and there will be 2 ducts coming out, and that will go and will be connected to a large chimney part. So that is how your ESP look like. The huge the sizes and very interesting thing, and almost, like I can say, in India 99% of the power plants have the ESPs. Okay, 99% of your power plants have the ESPs. So it is a very widely used process for the dust removal. Okay, let's see if we have anything more here, or okay, this is still a better picture from inside. Okay, so here you see here, well, pictures here, color is different than it's here. So this flue gas is in from here, and you see here the plates, okay, and this is one field and there is one hopper, and then what you see here are the wrappers that will hit to the plate to make it fall, and then you have the transformers and rectifiers to supply the order of 40 kV voltage to your electrodes. Okay, so this is how it looks like. Once the things fall onto this one ESP, okay, and then either it is pneumatically collected, okay, or I don't know if you recall, have you heard about the fly ash ponds and things like that? So then what they do is they put here and they bring a water pipe from here to here, and the water is mixed with the fly ash, and there is sluice valve which rotates, okay, and the fly ash keep on falling down, okay. So that thing, so you collect it dry or make a wet slurry, okay. Nowadays we only collect it dry because the dry fly ash is used in the cement, and you'll be surprised that well we can almost use about 30% content of the cement could be fly ash. So fly ash was a huge problem for the country because we are using the coal with a 45% fly ash, okay, and that always show up in your hoppers and things like that, and there was a huge problem. So DST come up with the government, whenever there is a huge problem they come up with a mission, okay. So DST made a mission called fly ash mission, and then they say well fly ash has to be utilized, okay, otherwise it's a problem. So fly ash is being utilized in the cement making, and cement people are very happy because they still can maintain the same quality of the cement, okay, that we can discuss because we also have done some work onto that one, and then fly ash is utilized. So to some extent we are able to resolve the problem of fly ash, okay, because we are almost generating about 85 to 90,000 megawatt of power based on coal, which is huge this thing, okay. So I don't think that's all I have in this picture, and then I want to talk a little bit something else now. See, again we are not talking mathematics, there is a great deal of maths involved in the collection and migration velocity and efficiencies and things like that, but I want you to know qualitatively and understand the physics, which we partly have done. One thing which I must tell you is the concept of the resistivity and the performance of ESP, because this is important. Everyone would, if you talk a little bit, that's fine, but if you slightly go into the details of the working of the ESP, is that people talk about the resistivity, okay. So we'll show you the concept of the resistivity here. So you have here electrode, you have here plate, let's say I just call this as X. We have talked about how big is the X? What, 3 to 4 inches, right? And then you see here what is voltage at my plate? It is grounded, so 0, okay. This plate is, and then you see here at the plate there will be some cake formation that will take place. So these are the particles, let's say, which are deposited. So this, let's call this the cake. Suppose I am dealing with a dust which has low resistivity, okay. So then because of if the resistivity is low, okay, and this is voltage here, the resistivity is low, then I have a picture something like this. The voltage will not drop so easily and something like this. If my resistivity is moderate, I will explain you what is the meaning of moderate. It may like this, and if resistivity is too high, then I get the picture like this. Okay, we are talking about low resistivity, moderate and high. Okay, and then to complete the picture, I must go, because here it has to be 0 and this is my 0 here. This also should become 0, this should also be 0. Okay. In your opinion, okay, which kind of dust I'll collect best? The higher one, okay, that is generally people have the feeling, but this is not correct. Okay. The moderate resistivity, let's talk, I'll give you the idea about the moderate resistivity, what this number really is. See here, when low resistivity is very low, see here, there is not much of the between here to here, there is not difference of the voltage. Okay. So as a result, the particles, even if they are trapped, there is not enough force for them, because things are about the same at this point to this point. So they have no enough force to get stick onto this one. So then when this your medium is the same, similar kind of voltage difference is there, so as a result they become re-entrained into the system. Okay, because they don't have enough force. So you have the similar condition here to here. Okay, there is not much of difference here. Okay, so as a result they don't find anything enough force to be attached to this one, then as a result they can simply very easily get re-entrained. Even if they have deposited, it's very easy for them to re-entrain. Let us talk about the high resistivity. The problem with the high resistivity is that, well, one thing is that the particles or the gas may not have the enough charge, the electrons may not be able to flow because of the resistivity they are showing. When the electrons are not flowing, they are not likely to hit to the particles and they will not be able to go through quickly from the medium and go and stick to this one. The larger problem with the high this thing is, you see here the voltage difference. Okay. Because of this voltage difference, okay, there is a possibility of generating back corona. Okay, because of the huge difference you see here and here. Okay, the corona we developed there, okay, at the discharge electrode, that phenomena can occur here. Okay, and if that occurs, okay, there is a fear that, well, the particles will not only dislodge themselves, okay, but then there is another fear that it can catch fire. Okay, because they, like at that point, so that can catch fire. So the ESPs, they work best under the moderate conditions. Okay, so then that condition is generally this one. So low resistivity, to give you a little feel, so what is low resistivity is what kind of particles are this one, like for example carbon particles, and there is an industry called carbon black industry. I don't know if you have heard about that. That they make the very fine carbon, and that carbon is used largely in that is used in making tires. Okay, the carbon is used a lot in the tire. So the carbon black industry, okay, that is to give you a little feel that these carbon particles will have very low resistivity. Moderate resistivity, like for example ash, and very high resistivity will be like, suppose there is sulfur dust and I want to remove the sulfur. It's just extreme examples that I am giving you. So if you are dealing with the carbon black, you go to the carbon black industry, they will not talk to you about ESP. They will talk to something back filters that we have not talked about. You go to other things where this one is there, the sulfur, suppose in your ore or in your process sulfur is there, they say, oh well, we are not going to use this one. Okay. So they don't use this one. So for the ash or ash kind of substances, it works very well. But unfortunately, Indian ash has a low resistivity. So that will fall somewhere in between. Okay. So therefore, the ESPs what we need in India, or what has been designed largely by BHEL and Thermax, is that, or largely by BHEL, is the size of the ESPs in India is very large. Okay. So some of the difficulties we had in India was in 1970s and 80s when we were importing the ESPs, and the Americans will make ESP based on their this thing. The science has really grown after that. So earlier ESPs what we see with the old power plants is a very small ESP, and that those never worked. And then slowly people realize that we need the larger ESPs and things like that. So now you will see a very large ESPs wherever they have, and BHEL is very leading manufacturer of ESPs. Okay. Okay, if you want me to show the removal dia, efficiency of removal as function of diameter, .25 they have the particles that we are trying to remove. So this efficiency is looks like something like this. This is a band basically. So some particles between 0.1 and 1, they have the minimum efficiency. Okay, and the particle smaller will have this thing, and then you see almost any particle with size of 1 micron and above will remove 100% in your ESP. But these some particles may have some lower efficiency. The next thing on the line is the most widely used process to remove very fine particles. Okay. Now after the ESP, which is something which is used, an application can vary from ESP to this thing. Okay. How this, again the physics part of the bag filter is something very similar to this. The bag is there, made of cloth, and the air passes through this one, and the particles will be retained, or something filter as you have done, as you have learned in the water and wastewater treatment. Okay. What is the physics? See, this is suppose fabric or my back filter particle. Okay, one of the particles onto this one. So my filter medium particle. So what are the mechanisms which are operating is that suppose the particle is here. Okay, so it travels. It will change the path, the streams will, the gas stream, okay, the gas stream, okay, then this particle because of the inertia will leave the path of the gas and get stuck onto the fabric filter, and the clean air stream will continue to go like this. Okay. What is this we call as 602, 603. The particle is moving because of its inertia. The gas will react to the disturbance. The gas stream will move up. The particle because of inertia will continue to move. That is called impaction, if you recall. Okay. So the mechanism, first mechanism is because of inertia. This is impaction, what I have talked to you. Okay. Second thing is, let's say a particle is very small, a very small particle. Okay, it will hardly have any inertia, Okay. So gas stream will go like this. This particle being very small, sub-micron size, 0.1 or something like this, this will have some kind of, what motion is that? Brownian motion. Very small particles will have the Brownian motion. So they can go like this. There is a possibility that the small particle can get stuck. Okay. So the second the mechanism is removal by diffusion or Brownian motion. For very small particles. Okay. You may have a particle which is fairly large. Okay, a large particle. Okay, but the density may be low. Okay, so its inertia will be low. Okay, so the gases are going like this. Well, I'll make it a little more bigger just to. Okay. Okay, but this particle, because of the low inertia, doesn't want to leave the gas stream, but you'll see the particle which is still with the gas stream may come in the contact of the filter medium. Okay, I'm saying the inertia is low, so it will not leave the gas stream. It goes along with the gas stream, but then it might hit to the filter particle. Okay, and then it might just be, because it might just get stopped onto this one. So that's what we call as interception. Okay. The another thing which is a possibility but low possibility is that these particles may be slightly charged. Okay, and with respect to this one, so there may be some electrostatic force that might be working between them, and the particle, as it is approaching this one, even if it is somewhere here, it just goes there. Okay. Three things are important. Fourth, which is not so effective in this case because we are not imparting any charge, is the, what did you say, electrostatic forces. The last one, okay, you have to tell me the last one, which is simply sieving as we filter a tea. Okay, you pour the tea, the pores are smaller than the size of the particle. So if there is another filter medium which is sitting here and the particle is much bigger, okay, then it's just stuck in between these two particles. Okay, so the another mechanism which is of not of great importance, okay, what is it? Sieving or straining, if you like. Okay, sieving or straining. So these are the, and the most important being these three things. Important mechanism. Okay. How the filter look like? Okay. Just giving some okay. your dirty gas goes in from here, and then this is your, these are your back filters. Okay, this gas, okay, and these particles, they'll make little cake onto this one surface. Okay, and the gas that has to pass through same way from here, same way from here. This gas goes on like this. Similarly from here, here. See? So what will happen? This is your fabric filter, like cloth, special kind of cloth, and so the particles will be stopped here because of some of these mechanisms here, and your clean air will come out of the simple thing. I mean, again, we are just talking physics, we are not talking the mathematics here. So then finally you will get the clean air that will go out from here. Okay. Okay. Once, what will happen at some times, where any filter mechanism is there, the pressure drop will slowly build up. Okay. When the pressure drop will build up, you will not be able to suck the air through. Then these things, bags must be cleaned. Okay. The way the bags are cleaned are the two mechanisms. One is reverse airflow. You stop this one from here, okay. Make the flow of the air reverse of the clean air. Okay. We will have the some kind of compressed air and things like that. So you make the flow reverse. Now the flow is from the outside to inside. So that will dislodge your dust, and the whole dust will fall into your hopper. Okay. So that is what we call as a reverse airflow. Okay. Second thing is, which is also very common, pulse jet. Okay. The fabric filter, as you see here, it is put onto a little steel cage. Otherwise, how this will stand? Okay. You can hang it up like this, okay, or you put a steel cage, put that thing onto there, as if you are putting a cloth onto the cage. Okay. So then you pass a electric pulse or some kind of pulse that will quickly shake the things very quickly, okay, and with a lot of energy. And then in the process of the pulse jet, all the dust will fall, and the bag will still again erect. So it is for the use. The thing which all things happens, electronically and with computer controlled, and so you can just remove the dust, as you see, and the dust will eventually fall onto this one. What else should I tell you about this? The dust falls into this one, and that is how you can, important thing. See, with latest design, okay, see, everything is basically in parallel. Okay. So if something is going wrong here, you will have to stop the whole thing. They can isolate each and every bag, okay, and they can go through when they are doing the reverse airflow jet, or when they are cleaning the bag, they can isolate certain area, okay, so that your whole thing is not stopped, because the size of the filter bag may be same size as this room. So they can isolate the bags or the section of the bag, because it's very common the bags get torn up, there some kind of leakages may happen something, or there may be some corrosion here. So but then they can isolate certain sections so that the whole thing is not affected. That's very important thing. So you have this particular idea, and if you see here, if you look at the collection efficiency and the particle picture, okay, efficiency of removal versus diameter. Okay. This picture also looks something like this. Okay. Particles with diameter 0.1 micron meter is removed with fairly good efficiency because of the Brownian motion. The large particles will be removed either by the impaction or by the interception, but the particles in between 0.1 and this thing, because neither this force is enough for them nor the Brownian motion is effective, so these particles which is in this range, okay, with little narrow range, will have the low efficiency for the control. So these particles are likely to escape. Okay. And I'll pass on the material to you from the email and things like that. You can have another look. Very quickly, let's do some comparison. Back filter and ESP. Let's talk the most important thing which we talk always is the pressure drop. Okay, now somebody tell me, where is the more pressure drop, in the back filters or in the ESPs? Back filters, okay, high. Delta P is low. What it means in terms of the cost? High running cost because I have to put the blower. So we say, well, high cost. Well, I have not talked to you about that, but what about the installation cost or initial cost? Where do you see the more? The ESPs, okay? I mean, we are talking in the relative sense. Don't say this is cheap, okay? Okay. Relatively between these two. Low initial cost. High initial cost. Okay. Given the type of the bag and the temperature, can all bags or the fabric, can it resist to all temperatures? No. Something is there, if the cotton is there, for example, if suppose the heat is very high, okay, it may not be able to resist that one. Okay. So this is, back filter is temperature sensitive. Okay. Depending on the temperature of the gas you are dealing with, your fabric filter quality of the filter medium and the fabric filter that we are using will change. Okay, that we are not talking about this one. It's not so temperature insensitive, if you like. Okay. What about the corrosive things? Okay, if you have the corrosive or high humidity, sensitive to because if you are not maintaining the temperature, the humidity, your water is always there in the combustion process, right? Flue gas will contain lots of water. So that kind of water may, if the temperature is low, that water itself will sit onto your fabric filter or making it non-operational. So it is sensitive to corrosion and high humidity. Not such a problem. the gases may contain the water, but it is in the vapor form, and it is in the form of the SO2 will not be in the form of the sulfuric acid, it will be in the form of SO2. And SO2 to convert into H2SO4 is very difficult.
Not H2SO4, sir. What about water depositing on the plates, metallic plates, and their corrosion may occur.
See, but then again, where is the S?
Corrosion we need just oxygen and water.
Yeah, the corrosions occurs, like, but then again the size of the plate you are talking about and the corrosion that occurs and makes a hole in the fabric filter. Okay, problems will happen, but then you see the long term thing, which the huge plate, steel plate will last, and the compared to this thing, that is in the relative sense, like huge plates are there, but some slowly corrosion is going on and things like that. Again there will be cake. Okay, that, and then how we stop the corrosion is by painting the things, and you see the cake itself will act as a resistive to corrosion.
Then one more thing is the running cost in case of ESP. There also we can consider it high because the power requirements is.
See, comparatively, again we are not giving the number, the question is well taken, but the cost of running this one is not so high depending on the power plant you are dealing with. That cost is very small, but here the cost of blowers, okay, and the pressure drop which takes this thing is really very high, like, and the pressure drop, the order of the pressure drop difference is so high that I don't remember the numbers. Here in the ESP there is no obstruction to the flow of the air, it just simply travels like in the duct, as if it is traveling in the duct, and here you see here every little thing has to go through this thing. So pressure drop is enormous here. Okay. So we talk about this thing, efficiency here, it almost exceeds 99.999. Very good, Anand. Practically everything is stopped. Okay. So that efficiency of the removal is very high. So whenever you are dealing with something most valuable, okay, you will always use the back filters. Suppose you are working in a gold processing unit and the gold is in the form of the particles, okay, you will not go for the ESP, you will say put the back filter. These costs are insignificant for me, because if little gold escape, then I don't. I am just giving you very the example which is kind of very coarse example, but then if you, for example, cement industry, because cement is a product, okay, so then they will have this one, because the efficiency of the back filter is high. Efficiency here is also high, of the order of about 99%. Okay. So depending on they both are comparable, you see here, but depending on what situation you are, okay, then you have to use this one. And that it is temperature sensitive, sensitive to corrosion and high humidity. Then what the people have done is the people use different kind of fabric filter. For example, if you use Teflon, what is the problem with the temperature with the Teflon? Okay, so depending on where you are, these back filters are there. But ESP is still considered to be more robust, okay, because here you see within no time you have to do the operation, maintenance, bag tearing off, the life of the bag, for example, the cost, running cost. See, bags will have the life, whereas the ESP once you install, you forget about for 10-15 years. The back filters, the fabric filter will have the life of 2 years, 3 years, 1 year, okay, and then you have to always maintain the inventory for that one, so you can quickly replace the bag, whereas the ESP, you make the ESP and forget about the ESP. But the other thing is that which we should not forget is low space. Low space is required, okay, this one, because you are increasing the surface area by putting n number of this thing, and then you can go vertically up. You have the back filter on one floor, second floor, third floor, and this thing, and because the ESP sizes are very large, so the space requirement is high. Space requirement, if you like. Okay, this is what are the differences and things like that. I think we'll have to stop there. If there's some point missing, I will cover that one. And then you can see the choice between back filters and ESP can be a little tricky one. And people, depending on what process they are dealing with, depending on what they want to remove, okay, they have this one. And then, for example, the other thing is this ESP, as we have talked about, this can be a little bit prone to fire. Okay, ESP, because you are dealing with electrons and corona and things like that, and then suppose there is a little bit more of carbon monoxide in the air and the temperature goes up at the corona, it can little bit explode, right. So ESP has another problem. If the gases are combustible or there is explosion that is possible because of the nature of the gases, you will not go for ESP. You will always go for the back filter, because there is no possibility of any chemical reaction as such happening inside the back filter. So that is another thing. People dealing with the air, the process where suppose the CO level is very high, hydrocarbon is very high, okay, then they will not go for ESP. There is a fear of some fire, but nothing to fear about if you are dealing with the inert dust like ash. So all the power plants in India has the ESP. But trends are changing because two things. Efficiency is higher, and some of the power plants which are very old power plants in India do not have enough space to put ESPs. Okay, and the laws are changing, and the government would say, or the law would say, well, we don't care you have the space or not, control the emissions or close down your plant. Okay, closing down of the plant is not an option. So even the power plants now, because of the low space requirement, they go for the back filters. Country like Japan, even if they have the ESP, they might still go for the back filter, because their land requirement, the space requirement is very, very important for them. Okay, we will stop it here.